welcome to What is Stoichiometry? Aside from a very interestingly weird word. So it's the ability to relate any amount of product or reactant to another reactant or product. This is a critical chemistry thing. If you say this word out on the street, people who remember chemistry will go, oh, that was a chemistry thing. Think about the difference between an element, like chlorine, a compound, like NaCl, and a substance, which can kind of be any one of those, just as we go throughout. So, originally, we've talked about these things being the quantity of compounds are defined by the coefficients. So, 2 hydrogen molecules and 1 oxygen molecule makes 2 molecules of water. We've talked about this in a singular fashion, but we can't even see molecules. So, we can relate this to moles. The quantity of compounds in moles are also defined by their coefficient. So 2 moles of hydrogen and 1 mole of oxygen makes 2 moles of water. Remember, a mole is a gigantic amount of particles, but that's what these are referring to. Just like a mole means this number, a dozen means 12. Those are all those relationships that we're going to use in order to use this effectively. So, we need to pick out mole ratios. These are equalities, they're conversion factors of how these things relate to each other. So, given a chemical equation that is already balanced, you won't have to balance them or correct them or do anything funny, they're provided. For every 4 moles of Fe, you get 3 moles of oxygen. That's modeled over here. 4 moles of iron for 3 moles of oxygen. For every 2 moles of the iron 3 oxide, you're going to be using 4 moles of iron. Again, that's that 2 to 4 ratio. We can also flip these. Remember, these are just equalities. So if these are equal, we can put whatever's on top and on the bottom. So we have our 3 moles of oxygen, comes from our coefficient, is equal to 4 moles of iron, also comes from our coefficient. So these are where we're going to get our new conversion factor. The rest are ones we've been using all along. So let's take a look at some examples. All right, so we're going to start off with what we're given, our 19.4 moles of iron. And we're trying to find out how many moles of O2 are used in using up all of those iron, because they're both reactants. So just like before, the unit that we start off with goes on the bottom. Now here's the difference, here's the key. If we're in moles, the mole ratio is a mole-to-mole relationship. So that means we can put moles of oxygen up top. That is our new concept. When you got moles of one thing, you can relate it to moles of a different thing. And, oh, I don't need that at all, because we're in moles of O2. So from our coefficient, we put in our idea, 4 from iron, 3 from oxygen. So multiplying that out, and I'm at 14.6 moles. That's not very practically useful because we still would have to determine either particles or mass. So let's look at a little bit further. So let's say we massed out so many grams of iron. And we want to know how many, again, moles of O2. You can relate any reactant to any product and vice versa. You can relate anything. Now, if I start off with grams up top, grams needs to go on the bottom. Grams are related to only one thing, moles of the same substance, in this case iron. Next, conversion factor. Whatever's on top goes on the bottom. So moles of Fe. Again, once I'm in moles of one substance, I can go to moles of another substance. The same numbers still come from the coefficient, 3 and 4. Remember, for every 1 mole, we have so many grams, which I've looked that up on our periodic table. 55.85 grams. Multiply across the top, divide by the things on the bottom separately, and you get 1.02 moles of O2. All right, let's take it a little bit further here. Another example. How many grams of iron 3 oxide reacting to 57 moles of iron? So 57 moles of iron is what I start with, what's given in the problem. And I'm trying to go to grams of this substance over here, Fe2O3. So moles are on the top, moles go on the bottom. Now again, I'm trying to get to a new substance. So if I'm in moles of the old, I can go to moles of the new. Fe2O3. Moles is not what I'm trying to find. That's why it's important to write what you're trying to find on the right to see how long you go. Moles are on the top, moles are on the bottom. And I can relate moles to grams of the same substance. This is just using what we've done before. The molar mass of that I've already calculated, 159.70 grams. And that's for every 1 mole. And our mole ratios again come from our coefficients. So 2 moles for iron 3 oxide, 4 moles for iron. Multiply across the top, divide by the bottom. And around 4,551 grams of iron 3 oxide. One more example. Going grams to grams, the furthest you would go. So 250 grams of my iron 3 oxide. And I'm trying to go to grams of O2. Grams are what I start off with. So grams go on the bottom. Grams are related to moles of the same substance. I'm not in O2 yet, so this would be your moles of what's your neighbor, Fe2O3. And once I'm there, I can relate moles of the substance I'm trying to find, oxygen. Moles aren't grams. Moles on top, moles on the bottom. So you always have kind of a zigzagging going on. To grams of O2. So there's 32.00 grams for every 1 mole. From our coefficients in the chemical equation, you've got 3 for oxygen and 2 for the iron 3 oxide. Remember, this was the same molar mass, 159.70, that we had before. And that's for every 1 mole. Multiply across the top, divide by the bottom things individually, and you should have 75.1 grams. Make sure you're using your own calculator to see if you'll get these same values, because it's pretty critical to making sure that you got this right idea. Off to our joke. The joke is a visual one. This is what molecule is made from bunny, oh, bunny. And that would be an ether bunny. Look up what an ether is and it'll make a little more sense to you. Answer the final question and come in with any kind of questions. We're going to get plenty of practice. See you soon. Bye-bye.